All right. Hello, everyone, and welcome to Handmade Hero, the show that we code a complete game live on stream on Twitch. No engines, no libraries, just us. And we are taking a look at absolutely everything that goes into making a game, right down to software rendering like they did in the old days. This is what we're working on right now. And like we talked about in the pre-stream, why are we doing this? Because, man, it is hard to find good low-level programmers these days. If you need one for a project that you're working on, good luck finding one. And so on Handmade Hero, what we try to do is encourage people to not be all about, let me go grab some library and I have no idea how it works, and I'm not going to try to optimize that because I don't even know what optimization is. None of that nonsense. This is all about if something needs optimizing, you are the guy who can go in there and no problem, right? So, with that in mind, let us get down to some optimization here. We are right in the middle of it. This is basically our first week of optimization, and we're just about to talk, well, not about talk, but to actually go do some SIMDization of some code. So let's go ahead and do that. If you want to follow along at home and you downloaded the source code because you pre-ordered the game on handmadehero.org, please make sure you've downloaded the latest source zip, and then what you can do is unzip day 115 source code. That's what I am on right now. All right. So this is actually going to be pretty easy because we set it up to do yesterday. If you remember, I'll move this over here, keyboard a little more centered. You will remember that we have our program here, draw a rectangle hopefully quickly. And what we did is we set it up so that basically there was a little block of code that happens for 4 pixels at a time. That's all math operations, and we were going to take that as the first thing that we needed to do so that you could see, I could show you very simply, how we turn some code into SIMD code using the Intel suggested compiler intrinsics that are built into basically any compiler that you're going to use these days. They're built into MSVC, they're built into GCC, they're built into LLVM. So pretty much no matter what platform you happen to be targeting, you can actually write code basically exactly the same as what I'm going to write today. The only time that you can't do this is when you have to port to like a processor like a Neon, like a ARM processor. But the concepts are still all the same, and so when we do look at a port, we will probably try to look at a port to ARM sometime in the distant future. We will show how to deal with that, but basically what it involves doing is just kind of usually just using some macros to switch from using the Intel intrinsics to using the ARM style intrinsics. It's not a whole lot to it. It's not like having to write a completely different piece of code, and there's a lot of stuff that just carries through. So anyway, that's what we're doing today. I want to do one simple thing first before we actually write those SIMD things, just so you can sort of see a little bit better what's going on. There's something that I wanted to do now. If you remember, we've got this going here. We have a little debug cycle counter thing that's telling us how many cycles are happening for our code, right? And of course, right now we were compiling in debug mode, so these are all kind of crazy cycle counts. So what I want to do is I want to just switch us back just for a second to running in the optimized build, right? This -02 that makes the compiler not do anything crazy and stupid. So basically, if you take a look at what our stuff is doing now, here you go, and what you can see here is the actual cycle count has gone up pretty dramatically from what it used to be, right? And the reason for that is because we've made this code a lot worse by me setting it up to do the SIMD, right? We have these ridiculous for I loops in there now, which are, you know, we've confused the compiler fairly heavily by introducing all of this extra stuff. So even though basically the same sort of stuff is happening, there's issues there. And also, the compiler would have to be very smart to figure out that, okay, this should fill matches with a bunch of other ones and stuff. So we've confused the compiler, so it's a lot slower than it used to be. But that's fine, because like I said, we remember what it was. It was like 200-something cycles. You kind of remember what we were doing there. It's not a big deal. But what I did want to do is I wanted to do something where we could do, without doing this count time block test pixel in here, we could start to time how many cycles per pixel this block actually did take over a wider range, right? And the reason for this, the reason that I'm thinking about this is because if you think about it, we're actually injecting, like this begin time block has to call an instruction to get the timestamp counter, and then this end block has to call an instruction to get the timestamp counter, right? It has to issue an instruction, and it has to issue some instructions to update the timestamp counter, and it has to pull in whatever that timestamp counter storage is in the cache, right? So if we did that on every set of 4 pixels, we're actually increasing the amount of work that we have to do and potentially polluting the cache, right? We're ruining sort of our loop by putting the timing into it. So what I'd like to do is move the timer outside, right? So that we have a timer right around the block here, like so, where we have a timer around just the block that actually does all of the filling, right? And I could even do it just so we're just around the for loops, right? So now we have test pixel there. And what I want to do, you can see if we actually compile it now and run it, what you can see is that we've got 2 loops that are basically, they're more or less the same. Here's the test pixel, excuse me. Here's the test pixel loop, and I should actually highlight these values. These are the totals. What is actually, you know what? I'm going to actually, we haven't actually needed to do this yet. I'm going to do this just so I can make it easier for myself to see which one is which here. We don't actually have names on these guys yet either. Here's my list of guys. So we don't actually have names on these guys, so it's kind of annoying to actually see which ones they are. But, well, I won't do it yet. We can actually see which ones these are at the moment, just by looking at the numbers here, so you can see. Later on, we'll do better debug counters. Don't worry, guys. But I like to focus on one thing at a time. So anyway, you can see here, number 3 would be test pixel, and number 5 would be draw rectangle, hopefully quickly. Now, test pixel is not really a good name for this anymore, so I'm going to change this one over to fill pixel, since basically we are filling all the pixels now. Or just like, let's just even do process pixel. That makes a little more sense. And I'm going to delete the other guys. Okay, so I'm going to go ahead and do it this way. And this will be process pixel. Okay, there we go. Oh, this is draw rectangle slowly. I forgot we had these in here. Get rid of these. There we go. All right, so now we should have, basically a listing here. So this one is, we never call the other routine, so we only have 3 and 4 here. This one is process pixel, right? And this one is draw rectangle slowly. So you can kind of see that they both get called 64 times, and obviously the total time for the routine is a little bit more per call, right? A little bit more. And that's just the setup cost, right? You can see that there's just a little difference between these two. That's the setup cost, and then this is just the loops. So most of the time is spent in those loops, right? So what I want to do now that I've timed the loop, right, in draw rectangle quickly, once I've timed the loop, what I'd like to do is I'd like to now go ahead and tell it how many pixels I did, because I know how many pixels I've done, right? I've got my ymin, my ymax. I know I do 1 loop through for each of those, right? And then I've got my xmin and xmax, and I know I do 1 loop through for each of those. So if I just multiply those two together, I know how many pixels I filled, right? It's just the area of that rectangle. So what I want to do is do an end timed block counted, right? Where I just pass in what I think the time actually was, and I have that do that. So it's xmin plus, it's xmin minus xmax plus 1, right? Because we're actually filling that xmax. We're actually looking at that xmax. And xmax, ymax minus ymin plus 1. I believe that's how many pixels we're actually filling there, right? And what I'd like to do is just go ahead and use that count. So what I can do is I can go into Handmade Platform, and I can take this macro that we were using to end the time block before, right? And I can do end time block counted, where I pass in that count, and then instead of it doing a plus plus on the hit count, what it'll actually do is just add the count to the hit count, like so, right? So that's pretty easy. I'm going to wrap that in a parentheses just in case there's anything weird going on there. And so, now when we run it, what we should see is we should see our fill pixel count counted much more more accurately. Okay, and now we see that has gone back to the value that we expected to have, which is much better, right? So I think that our test pixel must have gotten, the reason we were getting that weird 900 before was not because the compiler was getting too confused. I was kind of a little shocked that that was the case. It looks like we just misplaced we had still had the end in there in some kind of errant way. So now we're timing the whole loop, and then we're dividing by the number of things through it. And so now we're getting a value for cycles per pixel without having to time each individual pixel block, which takes a little bit of the inaccuracy out of it, hopefully, because now we know that we're not injecting, essentially, instructions into the stream that we are trying to time. Okay, so there's our 243 cycles per hit. And now what I'd like to do is I'd like to go ahead and show how to write some of this in SIMD. So what we're going to do is we're just going to take one thing first, and we're going to do the simplest possible way to write it in SIMD. We're going to take it one step at a time, very slowly. Now, you have to remember, for everything that yesterday we talked about, we're basically talking about registers that hold 4 values at once, okay? And so I'm just going to define one of those, oops, need 2 underscores. I'm just going to define one of those registers. And so I'm going to replace Texel AR, right, with one of those. And then all I'm going to do is I'm going to make Texel AR, I actually have to do it up here because this is where we first actually do it. I'm going to make Texel AR pass through the entire thing as if it is one of these registers. Okay? So I'm going to say Texel AR, define it up here, and I'm going to get rid of the Texel AR that we had. And so then what I'm going to do is I'm going to look in here, and you can see here's where we loaded in, and we're not actually going to write the loading code in SIMD yet, like I said, but so we're just going to take Texel AR and we're going to set one of the members of it, right? And the way that this works is there's actually this part, and fortunately this part won't persist for very long. This part only works on Visual Studio, on Microsoft's compiler. For whatever reason, Microsoft's compiler allows you to access the members of this thing as an index, whereas the LLVM's compiler doesn't have the same syntax for it. For some reason, they pick different ways. You can actually do it, but you can't do it the way that I'm doing it here. But I'm going to do it because it's a little easier for people to see. Well, you know what? I guess if I had to, I could do it the other way. Like, we could do it this way, right? We could change it to a float pointer, like so, and do it this way. So I'll do it this way just for the benefit of the people who are programming GCC. So there you go. Okay. So what this is doing is this is basically saying, okay, take the address of that wide value, that 4 wide value, and pretend it's a pointer to a float, and then you set the ith value of it, right? Because remember, these things in memory are just 4 values, so they can just be addressed exactly that way. Now, you don't want to do this if you're actually trying to write optimized code. So when we optimize this section, we won't want to do this. The reason for that is because we want to work with it in registers and do things much more efficiently than having the compiler have to do addressing in memory. But the compiler may actually understand this as well and do something smarter. We'll see. Either way, we won't be leaving this in, but for now, we'll do that just so we can not touch the loading code, if that makes sense. So that will put that in there. And then when we take a look at Texel AR here, what I want to do is take a look at everywhere that Texel AR is used. And what you can see is that Texel AR is only used there at the top in terms of modifications. And then down here in the bottom, you can see that it just gets read when it does this lerp, right, to produce the final Texel AR value. So what we can do is, for now, we can just we can change, again, this Texel AR here. We can change this use of it into that same way of accessing it, that Texel AR as a float. And then what we can do is pull just this computation outside the loop, and we can now do this, instead of doing it inside a loop for 4 values, what we can do is we can actually just operate on it as if it was 4 wide. And so Texel AR, which is now 4 wide, is just going to be a series of instructions that operate on this thing as if it were 4 values already, right? So I'm going to take 1 second here to actually do that, and then you will see what I am talking about. Okay. So this is the SIMD code that does exactly what we just wanted. And like I said, all we're doing is instead of putting that multiplication in there, mmmulps just tells the compiler, this is specifically the instruction I want you to issue. I want you to issue a 4-wide multiply of these two values. And then I want you to issue another 4-wide value of these two, right? Now this is a little confusing because we need to multiply by a constant here. And so what we need to do is any time that we were using a constant before, like inf255, we need to make a corresponding constant that is 4 wide of the same value. And like we covered the other day, we can do that very easily by just asking the compiler to generate one of those things that is basically just this single floating point constant broadcast to all 4 lanes. It's called a broadcast sometimes, but you know, just it's setting it in all 4 positions. So now we have a wide version of our inf255, right? And this is literally just saying, hey processor, please do a 4-wide multiply. PS stands for packed singles, packed single floating point values, and packed means 4. It was a bad choice. Pack is a ambiguous statement in this case, but that's just what they called it. So this is multiply packed and the 2 things that we're going to do. Basically, that's it, if that makes sense. I don't know why the compiler thinks we didn't initialize that value. I guess it's having trouble understanding what this is. So I will go ahead and temporarily just initialize it to nothing, but that's kind of annoying. Set1 PS. There you go. Are you happy now, compiler? Because we don't actually want to initialize that. All right. And when I run this, we can actually see that it's actually still producing the correct result, or at least, you know, as far as we can tell anyway. And we're good to go. Okay? So I'm going to go ahead and turn off for just temporarily, since we're not timing anything at the moment that we are looking at in terms of we're just working through the code. I'm going to turn on debug mode so you can actually see what's happening in there. I don't know why it never keeps our our render file open, right? Oops. It's hopefully quickly. Draw a rectangle. Location. Hopefully quickly. There we go. So what I'm going to do is I'm just going to show you what happens there so you can kind of see what's going on. So we step down here, and well, actually, I guess I could show you what happens here as well. So we step into, or I can't. I don't know why that didn't. Oh, because this is not a should fill. Oh, that's why it's complaining. Okay. It just doesn't like the fact that we're multiplying things that maybe we didn't fill. That's okay, actually, though. I mean, assuming we don't have any floating point exceptions on, we don't care about that because we wouldn't actually use the results. Yeah, I don't know how to tell the compiler that, but it doesn't matter. Anyway, let's actually step to where we actually are going to fill stuff in. And we can set a watch here on this TextLAR value, right? And you can see, if we take a look at the TextLAR value in Visual Studio anyway, like I said, it defines this as a union, so you can look at the actual values of it. So here is the F32 component. That's if you wanted, because remember, this is just, all this is a 128-bit value. And depending on what instructions we use, it chooses to treat it as one of any of these things. It could be signed 8-bit integers that are 16 wide. It could be 2 unsigned 64-bit integers, blah, 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 right? So it's giving us basically a bunch of options as to how we choose to interpret this thing because it doesn't know, right? And so we initialized it to 0 because the compiler was being whiny about things. So here is it initialized to 0. And as you can see, what we're about to do is load into the 0th member of it. It looks like the actual sample A value there is actually 0, so it doesn't actually set it to anything, so that's not very exciting. Looks like all of them are 0, so that's unfortunate, but that's just what it happened to be. So we're not actually loading anything in there. So that's not very much fun, and this is not going to be very much fun either. But unfortunately, that's just the pixel that we happen to have. I guess I could try to see if I can get to any non-zero pixels first, or I could set an if statement in there, I suppose. Oops, I mean to do that. Let's actually do if Texel AR dot oops M128 32 excuse me. Oh, right, I'm not supposed to do that. Float star. There we go. Okay. This will allow me to just set a breakpoint when we actually have a value in there. So there we go. So here's Texel AR, and now it's got some values in there. You can see that it has some values in there. Now remember, we loaded out straight up color values, which are 0 to 255, and we just turned them into floats, right? That's all we did. So they're not in the range of 0 to 1. They're still in the range 0 to 255. So what we're about to do wide is we're going to multiply, and you can see our constant here that we loaded. We are about to multiply this by this, and this is just 1 over 255, the inverse operation to normalize these ranges. And what we're going to do with this multiply is just multiply them all at once. And so there you can see them all, they all got multiplied at the same time. And then we're going to square it to do the light linear approximation. There you go. And so now that we've done basically what we were doing in a loop over 4 values, we just did all at once, right? It's literally that simple. That is the basic way that you SimDI's code, right? So hopefully that's pretty clear to everyone. There's really nothing fancy going on here. That's about it. And so all of this stuff, AG, AB, AA, and so on, we can actually do exactly the same way. So if you take a look here, we can also do AB in exactly the same way. And we can do AG in exactly the same way, right? I guess I should put these in the right order there. AG in exactly the same way, like so. And we could even make this, you know, a little bit clearer by adding a square macro. We could have kept this, we could keep this exactly the same way that it was now, right? By doing a, like a, you know, some kind of an square thing, right? That would just go around this and do the squaring for us, and it would just look like, you know, define square A would just be equal to the call to mul_ps, right? Would just be that. So you can do all the same stuff that you would have done in here, and so I think that's a little clearer, right? Does that make sense? Pretty straightforward. So we can actually make our own macros or make our own anything. You can even make your own functions, inline functions. You can use these things any way that you really want to. There are some caveats that we'll get to a little bit later with alignment, but for now, you can just think about it this way. All right. So that's pretty much all we need to do there, and we've got a different thing that we were doing here to Texel AA, which is we were just doing this mul_ps on it. We were not doing the square, so we want to make sure that we handle that properly. So there's our AA. And so that replaces essentially all of this code, right? All of this stuff that was happening in the loop can work that way, right? So what we want to do here is convert texture from 0 to 255 sRGB to linear 0 to 1 brightness space, right? So that does this. And we're going to do this exact same thing for all of these guys, right? We're going to do this exact same thing, Texel AR, AG, AB, AA. We're going to do that for the B version of all of our stuff too. So we could literally just duplicate this, right? And off we go. So in here, Texel A becomes Texel B. In here, Texel A becomes Texel C. And in here, Texel A becomes Texel D. And now you can still see it. And we could even collapse this further. We could make a little macro to do this whole thing, which maybe we want to do. But I'm going to leave stuff a little expanded right now, just so people can see it. Because for people this is their first experience with this, it may be a little confusing, and I want them to be able to see all the instructions, so it's not all hidden up in any complex way, right? So all right, that's all of these, right? All of this stuff now can go away basically, and then all we have to do is change these guys to actually be using this sort of float load. But I'd rather not do that because I feel like it'd be easier for us to actually just do this operation wide as well, right? Because we kind of know, I've shown how to do them now, so we don't really need to take quite such baby steps. We could just make this whole thing be wide as well, right? So what I could do is I can go ahead and take this guy out here. We can start to loft these guys out and make these guys wide. Is that too much? I don't know. I don't want to go too fast for people. So what I could do, here's what I could do. I could do like just something like a simple macro to help us at the moment, where we do something like this, and then all that is just whatever the thing is that we were talking about. It takes the address of it, and then accesses the ith value of it, like so, and then I could do this a little more straightforward, right? Does that make sense? Hopefully that makes some sense. And that would just mean that we can take this one step at a time. I don't want to like SIMDize the whole thing and have everyone get lost. So what I want to do is make sure that I go at a speed that everyone can follow okay, and see what we're doing step by step. That makes sense. And then, once everyone's kind of comfortable with this, then we won't in the future spend a lot of time doing things in in a step-by-step fashion. Maybe we'll jump a little further and maybe do a little more of like just go ahead and do it, and then we'll debug any problems that we have, step through it kind of thing, rather than taking it sort of piece by piece. But the first time out, might as well go slow. Excuse me. All right. So what we have to do now is we have to, and I kind of want this to happen everywhere here, right? So what I would like to do is I would like this to be up there, like so. And so that way we can also convert all the rest of these. So if I do mi that, I can now, convert all the rest of these so that everything in the Texel set is in a proper M128. This is probably something I should have made a macro for just now, but what are you going to do? I'm having a bad typing day today. The problem is this is a very narrow desk that I have in here. It's just a little, it's not even really a desk. It's this cheap thing I bought on Amazon to hold the Handmade Hero thing off in this side room, because it's not a very big apartment, and so when we do Handmade Hero, I try not to drive my wife insane. So I don't do Handmade Hero out in the main room of our apartment. So I bought this little, it's kind of like an artist's easel thing. Drafting table, that's what it is. All right, so where is our M? Let's put that up there. Okay. Just need to put that a little further down. There we go. And all of these guys now have to be defined as actual M128s. And unfortunately, that means I have to do this, so the compiler will keep complaining, which is annoying. But we can fix that later. And it's totally fine for the compiler to complain. It's technically correct. We have some stuff that we're going to need to do. It doesn't really understand how the pixel setting and getting like masking and stuff works, so we'll deal with that a little later on. That's not really our primary concern right now. Primary concern is just converting this code into stuff that operates wide, and then once we're done with that, we can worry about the actual mechanics of getting it to produce good code that's not too far off of what the assembly language should look like. Okay. So now, as you can see, we're running just fine, even though we have compiled in a fashion that is now doing everything completely wide for those texels. So now all of this stuff has been moved outside of the loop, which is great. We're getting there, right? So all this stuff that used to be done in a for I loop is now just done in one go per guy that does all 4 of the pixels. So what we want to do now is, again, we want to just kind of keep moving things out here. We want to keep making things more wider than they were. So what we want to do is continue along. So I think I'll start with FX here as well, these guys. So let's go ahead and make those wide. Okay. So everywhere that those are used, again, in this routine, we will loft those. We will let the macro take care of those. But then when we actually go to use them down here, we want to make this stuff kind of, again, loft back up. So what I want to do is I want to pull this whole thing out, right, like so. And that actually, you know what? Let's just do the rest of it here. Let's also do that part. And then this part we will still do in scalar, right? Like so. So there we go. And the reason I'm stopping here is because this clamp is something that I want to talk about a little more specifically. Because I don't know if you remember, but back when we had it in there, the reason that I didn't expand out that clamp routine into a real routine was because I wanted to talk about how to do it in SIMD in a different way, right? All right, almost there. Okay. I think that's everything that needs to happen down in there. Oops, no, I missed one. There we go. So now those are all working okay in there. And so now what we need to do is we need to make all of this stuff be SIMD. So these guys are new, right? All of this stuff is new. So we need to actually define new things to hold it. The same is true of these. There we go. And now some of this is trivial, right? So we know this guy right here. We know to modulate the incoming color. We've already done this. This is just an MMLPS, right? So what we need is we need our color value, our color R. We need a 4x version of that, right? That incoming color value, we're going to need it to be blown out. Because basically, anytime we multiply by some constant that gets passed in, we need to now have a wide version of that constant so that we can multiply all the lanes of what we're working on, all 4 pixels at once. So typically we just take all of those inputs, like those color values, we take them all and we blow them out, right? So you can see us doing that, right? We've got, let's see here. Is color 32? What is color 32 still doing there? We don't even use that. So we have this color that comes in, right? And what we want to do, again, is we want to sort of prep those wider versions of the thing. So we've got that here. And because we know we need all of these constants, I'm going to do the other ones we need here. We just need the value 1. Just see in a second. We're going to need that. We'll probably need the value 0 as well. And now sometimes there's ways people like to generate these in different ways. Like you can generate 0 in a different way by XORing a register with itself or stuff like this. We're not going to talk about that quite yet, and we may never because it's not necessarily the kind of optimization we're doing, but point being, for now we can just create them as values. So what we want to do is we want to take this color value that we have here, and we need each of its corresponding versions. We need color R 4x, like so. And by the way, the 4x prefix suffix I'm going to drop once everything is entirely done in this. So I was just using it to make sure that we don't name conflict with any of the existing ones. So here we go. I'm literally just preparing replicated versions of these so that we can just multiply by a replicated version of the constant, like so. So that the code still looks nice and simple. Okay, and so we've already done this guy, the MulPS. If we take a look at what's happening here, again, this is exactly the same thing. This is a really, really straightforward thing. for us to do, right? All of these multiplications, they are just literally multiplications, right? So we can trivially turn them into this. There we go. Again, I'm doing absolutely nothing here other than rigidly translating any times symbol that you see into a mul PS, right? That is now macroed. And then the pluses, exactly the same thing. We haven't done an add yet, but an add PS just does the wide add as well. And what you can see is we're summing 3 values here. So I'm literally just going to do 3 add PSs, right? Add the first 2 together, add the next one, right? And then add the next one. And that's it. So that's the complete SimDI's version of that. And we can actually make it a little bit clearer potentially by doing this. So you can actually still read it, right? But, you know, I don't actually care about that, so I'm just going to leave it this way. So that's really all there is. And this, I guess this whole thing is just, you know, an ABCD with the R value there. So I'm just going to duplicate that since it's the exact same thing happening each time. It's R, G, B, and A, right? R, G, B, and A. R, G, B, and A. G, B, and A. G, B, and A, right? So that's the complete bilinear operation there. Does the blending. All done. These guys, again, if you want to subtract, sub PS, so add and sub, literally nothing to it. We've got it this way, but of course you can't use a constant here. You have to use an actual wide value, but we have a wide value, right? We have the constant 1 that I already defined, like so. And so that subtracts those values from 1, again, 4 wide. And then finally, we've got these guys. Again, pretty simple. This is just a mul, right? This is just a mul. Really straightforward, right? Okay. Oops. All right. So now we've converted a much larger chunk of this routine. So all of this stuff is now happening in SIMD. And let's see if we made any mistakes. Looks pretty good to me, right? Still all pretty kosher. So here we go. All we have to do now is kind of push through to a few more. You can see leaving the clamp in there. If we don't look at the clamp, if we ignore the clamp, we should be able to actually do the rest of this as well. So let me go ahead and grab out everything other than the clamp, put it out here. So we're just left with the clamp. And so all of these things we should be immediately recognizable to you. If you take a look at this, you should be able to see that literally all this stuff can be done wide with only the stuff that we already did, right? We have an square that we did, which is just that mul. We have the inv255 4x version, so we can do that wide. So these should be, like, by now, hopefully everyone could just do exactly what I'm doing, and there's no mystery to it, right? It's literally just totally rote transformation, nothing interesting at all, right? Just totally basic, totally easy. Okay, so there's that all happening 4 wide. Again, we can do this 4 wide because it's the exact same stuff. Always forget that second underscore. This is going to be a sub, right? It's going to be a sub of 1 and Texel A, like so. And then these, again, the blendeds are going to all be exactly the same as well. So we can get rid of all of these i's. And these are all just going to be, again, muls. These are muls with inv Texel A. And these are just now don't need to be accessed by element anymore. They can just be done 4 wide, like that. So now that's all done 4 wide as well. This is done 4 wide. And finally, these guys, again, really, really simple to do for wide. We've got a constant here that we need to do. Excuse me. And so then the only thing we need that we don't have yet is that square root. So we're going to leave that square root in there just for a second. Okay. All right. So to sRGB 0235. There we go. Sorry, I'm still a little bit allergy-ish. I'm not sick. All right. So the square root here, we're fortunate that even though it's a little bit slow, there actually is already a. We can go to that Intel Intrinsics guide, and you can see right here that we actually do have a square root. In fact, if you search for square root, you can see all of the options that you have for square root. Right now, we're going to take the easiest option that's available, which is, I believe, there is a mm_squirt PS, which again isn't necessarily the fastest thing we could do. We'll have to think about it a little bit more if we want to do anything fancier here. But for now, we'll just do mm_squirt PS. It literally just does the square root for us. So let's go ahead and put that in there. mm_squirt PS, squirt PS, like so on. Right? And so now we have to go ahead and convert some of these variables because all of these are now wide as well. Right? And done. Right? So, finally, once I'm done with getting the accessors in here, we should be able to run this, and it should be now wide everywhere except for the clamp. Oops, I left a plus in there. Who did that? That is not how you do it. There we go. So let's make that happen. Okay. So it looks like we forgot one constant, and this guy needs to be accessed via the M. And then, hopefully, that is it. All right, so 155, oops, is just that. Oops, forgot my 4x. Okay. So if we run that now, again, we are totally blitting correctly as far as we can tell. And we've almost SIMDIized everything except the load. Basically what we have to do here is get the clamp working. So the clamp between 0 and 1, if you remember, we've got this math code here, right? And we have clamp 0 to 1. And the way that was working is it basically does a bunch of work here, right? And so what I want to do is I want to sort of, I want to do something where we can actually take a look at what code that was actually generating. When we actually do this, right? And so what I'm going to do is I'm going to try anyways to see if we can see what that does in the optimized build. I just want to show you what's actually happening there. I don't know if we'll be able to or not. I'm not sure how easily I'll be able to point out what's going on here. But so we're in the optimized build now, and so we're gonna jump in here and see if we can look at at the clamp. So let's see. So you see how we come in here to this clamp, and here we go. We're loading some stuff in here. Let me get out the registers window so we can take a look at it. So of course, unfortunately, probably a bunch of these values are 0 since we're up on the first pixel or whatever, which is usually a 0 pixel because it's it's not inside the filled region of the sprite. But if you take a look here, you can see that we've actually got a bunch of jumps that are happening in here as well. And what's happening, I mean, it's just kind of hard to see what's going on here. But you can see that what they're doing for the clamp is it's actually doing those if statements, right? And you can kind of see it's got XMM6, it's got it loaded with 1, and it's got XMM 7 loaded with 0. And what it's doing is it's actually doing jumps based on whether or not it thinks it needs to replace the values or not, right? Based on whether it thinks they're out of bounds or whatever, which is not what we would want it to generate. Like, we don't want it to generate those jumps. There's no reason for that to happen at all. Like, we shouldn't have all of that there, right? And so that whole kind of situation is not at all the way we want it to look. What we want it to do is do something much more straightforward. And so that's what we're going to do. And you can kind of see it continuing to do more of those clamps here, right? You can see it doing them, clamping by doing the jumps, right? And so the reason that it's clamping, the reason that it's doing clamps by jumps is because that's what we actually wrote, right? We wrote like comparisons. So it's doing sort of literally the structure that we have here. It's looking to see if it needs to do this operation, and if it doesn't, it jumps over it, looks to see if it needs to do this operation. If it doesn't, it jumps over it, right? And so that's much less efficient than we would like it to be. What we can do, because now we know we're operating in SIMD, what we can do is we can use functions that are built into SIMD, which actually do a comparison plus a replacement in one operation that's actually extremely fast, as you can see from the tables, throughput 1. And so what this instruction will do is it will take two values, it will compare the two values, and it will keep in which, for each lane, so 4y, it's doing 4 of these at a time, it compares each pair, and it'll keep whichever one is the minimum. And similarly, we can look at the one here, which is the opposite, which is the max. It'll keep whichever one is the maximum, right? So if we have a way to compare and keep only the minimum, this is exactly what we were doing. We were comparing and keeping the smaller of the two values, right? If result is the smaller value, right, then in this case I should say maximum. If result was a smaller value, we keep min, right? And if min was a smaller value, we keep result. So doing the clamp to the min just is doing a max between result and min, right? And similarly, this guy was doing a min between result and max. So if we just do the min and max, we can do two very simple instructions, no jumps, to do that clamping, right? So all we need to do here, right, to do these clamps, move them outside, get rid of the loop, right? So in order to do those clamps, all we have to do is first make sure we clamp from 0 to 1, and then, first make sure we clamp to 0, and then make sure we clamp to 1, right? So we just do an max PS, right? And we say that we want to keep whichever value is larger, Texel R or 0. So if it's below 0, we keep 0. If it's above 0, we keep Texel R. And then we just say, well, and also we do a min PS, right? To say we'll keep whichever is smaller, the value that comes out of that clamp, or 1. Does that make sense? So we're just basically using min and max to do that clamp with no actual comparing or branching on the values explicitly because it's actually done just as part of that min and max operation that's built into SIMD. So we can just use 2 instructions to do that clamp, and that's why I say that the clamping is very cheap when you're in SIMD. That's basically 2 cycles to do a clamp between 0 and 1. Very, very straightforward operation. Okay, so we got rid of all that nastiness. It's gone now. And here we are. And I want you to notice something, too, about what's going on at the moment, right? So in the compiled build here, you can kind of see that our cycle count's already going down, even though the only things that we've done so far, we haven't even optimized the load. We've just made that backend happen more SIMD style, right? You can see that our game is already starting to run faster in the optimized build. That cycle count is now down to once it's below 200. It's now down to 175, 179 cycles per pixel, right? It's still not where we want it to be per pixel, but it's getting lower, right? And so the last thing that we might have to, that we need to think about here, I'm not sure if we got time for it. In fact, let me see if there's anything else we can do besides that one. But I don't think there is, unfortunately. Let's take a look here. Well, you know, we could do some of these guys wide. Let's do some of these guys wide, and yeah. Yeah. I mean, basically, you know, I said it was going to be easy. Hopefully you agree that it was easy. Now that you kind of know that we've got these intrinsics to do multiplication, subtraction, adding, we know that they just turn into single instructions in SIMD that are very easy to understand. Hopefully you can see that programming literally what the processor was going to do, almost down to the assembly level. We didn't quite do like register assignment or anything like that, but we did most of it with the intrinsics, was very, very straightforward, right? And so the hard parts are what we have left. I don't really know that I want to try to start tackling them now because we only have about 5 minutes left, so I think that would be a bad idea. But basically what we need to do now is we need to tackle the thing that fills, so basically the thing that writes, you know, the pixels back after they've been blended, and the thing that loads, right? And the load's going to be the really nasty one because it's got to do all this texture lookup as well, which is inherently not SIMDable. Specifically, this part right here is super not SIMD friendly. So yeah. What I could do just in the meantime is we could SIMD a little bit of this, like our V2, our pixel P and so on. We could do that in preparation. I don't really know that we even want to do that. I have to think about that a little bit more, but we could do it now since we've got 5 minutes left and we're sort of on a bit of a bender here. We might as well go ahead and do that. So if I was going to do these guys wide, let's first change them into scalar equations so we can see it. So here's pixel P x, pixel P y, right? There's the x value, and there's the y value, like so. And then if I were to do a dx dy, that would just be that, correct? Let me see where we're at here. That's got to be a float conversion there. So does this. And there we go. Now we have to convert these guys to that as well. So we have an inner product, and we know what the inner product is, right? The inner product is just each of the components multiplied together, right? So it's just that dx times x and the dy times y. And similarly in here, we would do the exact same thing, right? Again, I'm just expanding out that inner product, dy times y, oops, dx times x, dy times y. And there's everything there done in scalar. And let's just make sure it's correct. It looks pretty good. Why is this running so fast all of a sudden? What just happened? Our speed just doubled from me doing that? Does that make any sense to you? I don't know. Okay. What just happened there? I am so confused by what just happened that we have just... That is what we are figuring out right now. Did I accidentally compile somehow differently? What on earth did just happen? Let me see. I would really like to know what just happened there. Okay. So was that literally the entirety of... So that's 178 cycles per pixel. I switched to doing just that expanded out, and we dropped to 125. All right, I'm not imagining anything, right, people? You're witnessing that. This is literally the exact same code, almost in the exact same way. What is the compiler doing? Please tell me what the compiler is doing to blow 50 cycles on the same piece of code. It just full-on inserted 50 cycles of nonsense, apparently. What's it doing? Show me the disassembly. All right, so here's this branch. I don't see anything particularly weird there, do you? I mean, convert Q, move SS, sub SS. I'm not... I have no idea what would be causing 50 cycles. Of stuff there. Well, all right. I mean, I'm just gonna do, you know, I don't know what's happening, so I'm just gonna take this and I'm gonna copy it into the scratch buffer for now. So there's the slow one, right? And now let's take the fast one. Maybe it optimized out something below it or something. You know, could be the case. Oh. Oh. Do you guys see what happened there? It lofted this stuff outside of the loop, I think. I think it just literally folded this stuff in. Did it change the loop condition? I'm perplexed. But you can see that this code is completely different. It's doing nothing even close to what it was doing before. All right, there we go. So you can see that it's still doing the bottom part. So it's still computing U and V, but it is now no longer doing any of the other work. It is not doing any of this. This stuff has gone away completely. And I guess... So RBP minus 80 into XMM2. So I wonder what it's actually decided to compute here. I'm not sure. Move X, let's see. Can I take a look at XMM2? Oh, I can't do that? I was hoping I could. Guess I can't. I wanted to view it as a float. PP, R14D. Move demos, so that's actually up converting, convert DQ to PS. That's converting, I believe, the integer to the float there. Doing the sub, so it's doing this. I think it's doing this calculation here. It's the pixel PX value. So I think, I could be wrong because it takes a while for me to read assembly. I'm not the best assembly guy, but it looks like what it actually did was it went ahead and moved out the pixel P to not actually have to happen. It looks like it maybe folded that in to the outer code and doesn't actually, it couldn't figure out for some reason how to do that here. I guess because of the v2i was confusing it. I don't know. I mean, that's the only thing I can think of, is that the v2i or the inner, I suppose, was confusing it. I mean, I guess without a little bit more forensics, it's hard to know exactly what it did. We'd have to look at the whole loop and decipher what everything was doing. But I guess this is just a useful lesson here to mention briefly before we even know what exactly the compiler did. This is kind of what people joke about when, people often say that you see programmers talk about, in C++ and stuff, they're like zero cost abstractions, oh, it's an inline function, or I wrapped it in this class and that it's fine, doesn't cost anything. So hopefully you can see what a load of bullcrap that actually is. That is an example of literally just taking an inline function that was 2 multiplies and an add, and another inline function that was a cast. That's it. Just that. It was enough to confuse the compiler out of 50 cycles of optimization in a 179 cycle routine. Like a third of the cycles, well, a quarter of the cycles of the routine were saved by simply getting rid of 2 inline functions that the compiler had complete knowledge of. To quote Fabian Giesen, when he was complaining about something like this just recently, on Twitter, I think he posted, "Tell me again about your zero cost abstractions." And then he posted some timings that showed that some very straightforward things of putting something in like an inline function or something ended up costing him huge on some stuff, and blowing it out didn't. What can I say? That's just the way it goes, right? That's pretty spectacular. I don't know that we want to go through the assembly and actually figure out what it did. If anyone wants to, you're welcome to do so. You've seen both code paths now. But that's pretty amazing. So anyway, sorry that was a little bit of a sidetrack. I'm going to take just 5 more minutes real quick here. We'll still do a Q&A, but I'm going to take 5 more minutes real quick just to finish doing the SIMD that we were going to do here, lofting that outside of the loop, just in preparation, which actually might make us slower because it looks like, I mean, maybe I'm setting up for doing the final thing that we want to do. But basically, what I wanted to set it up for doing the rest of the SIMD stuff. So we're at 125 cycles now. We might actually get slower. But what I wanted to do is I wanted to move these guys outside of the loop, right? Because we can calculate all of these in SIMD as well, right? Let's see here. What I want to do is say, okay, let's make dx and u and v and all these guys. Let's just make them wide, right? So here's a M128 for u, and that's going to be mm mul ps dx like so. And that's going to be a mul ps of dy like that. That's going to be a mul ps, and this is going to be a mul ps like so. And these obviously have to be 4x's, right? These are those axes as constants. So we got to make those constants. There's a M128, and I guess what I could do here is I could make them right here, and then we can just copy them out. So there's that 4x is just going to be mm set1 ps of nx axis dot x. There we go. So I'll put those out here, like so. And once we've got that, we got to do our add ps to add these quantities together. Thank you, Emacs, for that helpful premature indentation. And then this is going to be an sub ps, sub ps, and this is going to be another constant, origin x, set1, block that out there. Okay. Yep. And we will grab this guy, put that up there. There's our origin values. And so now all we have to do is compute these pixel ones. I guess for right now, I'm just going to do an set1 ps of these guys. I'm not going to think too hard about this, but we'll probably want to do something a little bit smarter for that. Oh, sorry, it's not a set1 ps actually, because it needs to be, the y value is, but this guy needs to be the different values, xi plus I. So what we need to do there is load in for pixel px. We can do an set ps again. We can do something a little smarter here later, but for now, let's go ahead and do it the obvious way. Now, like I said, I always got to check this because I get bitten by it a lot. We want it to look like this in memory order. So we want the low value to be xi plus 0, then the higher going up in the registers. And I think set ps is written backwards from what I usually want it to be. And it is. You can see it does 3, 2, 1, 0. So I want it actually like that, if that makes sense. So yeah. Did I spell those wrong? NX axis. Oh, I didn't do the y-axis. There we go. Okay. And so finally, inside of our slow part of the loop here that we have not actually done yet, we need to access those values, the u and v values, by their I. And similarly, we're going to have to do any of these other guys. Will have to be done that way as well, who are using the u and the v. There we go. But now we've got a little bit more outside the loop there, so we're still, we're creeping forwards. And there we go. All right. Now, I'm going to bring the episode to a close here. It's hard because I like doing this kind of stuff. For some reason, I like doing these transformations. I don't know why. Probably because I don't do them that often. I don't optimize stuff in SIMD that often. Ironically, or oddly enough, I happen to be doing a bunch of that this week for The Witness, but that was random. That's not the common case. So anyway, we've gotten it down to where we just have this one loop here that is not SIMDized, that's at the top, and that's where we're going to have to do a little bit of work there to load everything in. That's going to be a little annoying. And then we got this pack. We'll probably start on Monday with this repack here, because that's going to be easier for me to sort of explain and walk everyone through. It's going to be easier than the Texel loads. So we'll do this one. But as you can see, we're getting much closer to having an entire SIMDized routine. And hey, guess what? Looking at the cycle counts and the speed, the game already is now back to running in real time. I don't know if you noticed that, right? We are no longer slow, right? And so that's pretty awesome just in and of itself. We haven't even really done anything too serious to it. All we've done is just the rigid transformations that hopefully, now that I've explained them to you, anyone could have done those, right? I didn't use any special processor knowledge. I didn't use any special experience. I literally just did a series of transformations to that code that I think, now that I've explained them, any of you could have done based on just the explanation that we had yesterday and today. There was no experience or finesse necessary. You did not have to be some kind of optimization whiz to do any of those things. You just had to go, okay, I'm going to change this routine from doing 1 pixel at a time to doing 4 pixels at a time just by widening all of the operations to 4. right? So hopefully that was easy and comfortable, and it might have been a little scary and weird to you at first because, yeah, I mean, you've never seen any of this stuff before perhaps, and that's fine, but, now that you're looking at it, does this look that strange? No. It's just, all it is instead of putting plus and times in between things, you see mul and plus. And what you may, you see mul and add and whatever, right? But that's it, and it's really easy to read if you understand functions at all, right? Now, there is one thing which is like, hey, you could use overloaded operators or something to make this easier to read. The reason I don't do that when I'm SIMD optimizing is because I am terrified of what the compiler will do. And I think, hopefully, based on what you saw today with that simple change we did up here, remember saving 50 cycles, and it was just a change from using an inline function to actually writing the stuff out. I am terrified in optimized code of the compiler doing stupid stuff, because it always does. And so when I care about a routine being optimized, I want nothing that doesn't have to be there to be there. It's a small price to pay to just write it out this way, and then I know the compiler is not going to do anything too dumb, although sometimes it still does some dumb things. And so that's why I don't like overload operators for this, because the number of routines that we are going to optimize at this level is very small. They're basically just going to be a few pixel filling routines probably, and we won't do probably that much more in SIMD. So it's a small price to pay to just have to do it out this way once or twice, and then the compiler is not going to ruin your life in some bad way that you weren't expecting, right? So there we go. So let's go ahead and go to the Q&A. There may be some things that were confusing people today, so that's I just want to give a little time for questions, and we will see. How do you cover multiple CPU technologies intrinsic-wise? Preprocessor switches on dedicated intrinsics for each. Also, whom to read on ASM? I'm thinking Mike Abrash. So Mike Abrash probably isn't super useful to read on ASM anymore because all of the stuff that he wrote was prior to Wide. I don't know if Fabian's got some good stuff on SIMD. I don't really know. I'm sorry, but I'm not sure. You'd want to read someone who talks about SIMD because SIMD is very different. And a lot of what you have to do doesn't have anything to do with the stuff that Mike Abrash was talking about, which is like filling UNV pipes and stuff on a Pentium, which isn't really that relevant anymore. Occasionally it's relevant, but it's way down the line on things. It usually tends to be more about making sure all your stuff lines up in lanes and stuff like this. So I don't know. As to how you cover multiple CPU technologies intrinsic-wise, yes, the answer is you use basically what we will do when way down the line when we get to that is these intrinsics we will just define our own versions of. So we'll change it to something like our own mul ps or some or our own like mul 4x or something, and then we'll just pound define that to be the right thing for the compiler for the particular platform, right? And it's kind of a pain in the butt. But it's not that hard to do. HAUB, we have come from 385 cycles to about 123 cycles. Does something like the 80-20 rule apply? Do you think we will get down to 50 cycles? Yes, I do think we will get down to 50 cycles. Well, I don't know yet. We haven't done our estimate. So again, like I was saying, what we need to do before we can really say what we'll probably be able to get down to is we'll need to take a look at all these and count the operations that we have here and see what our maximum throughput would be, and then we have to figure out whether or not we could hit 50 cycles, right? What you can see is even if we just start to count them now, right? We've got 1, 2, 3, 4, 5, 6, 7. So 7 times 4 there, I guess, is like 28. So, looking at this here, that's 28, and that's going to be about... looking at this, I think it's pretty clear to me that we will be able to get this routine down to 200 cycles. And 200 cycles is, for 4 pixels, is 50 cycles a pixel, right? So really my primary question is going to be what happens right here. So I think the answer is, will we be able to get the math down to 50 cycles per pixel? Absolutely. I think we're on track. Will we be able to get the Texel fetch and unpack down to under, when L added up to be under the 50 cycles per pixel? That's going to be the real question. So this is the guy, and I don't know. It's premature. But just spot checking the number of multiplies, I think the number of multiply adds in here, will we be able to get that down below 50? Absolutely. Because, again, we only have to get it to 200, and we're doing 4 pixels at a time. So getting from 200 to 50 won't be, if we get it to 200, that means we're at 50 per pixel. The way we use mm², does it calculate the argument twice? It shouldn't, but we should definitely verify that. That's a good point. The compiler should do common sub-expression elimination pretty well. But, that's a very good point you bring up. We should definitely check, right? So let's see if we can determine that from looking at the instructions here. So it's going to, wow, it's done a bunch of folding of this, but all right. Let's take a look here. So it looks like it is doing the squares. Let's see here. It would be nice if we could see this a little bit better as floating point values. So we're doing move in, move in, move in, move in. Excuse me. It looks like this is loading 255. Where is, so XMM3, where is our, we need our inf255 4x in here, or did it just leave that in a register? Is XMM3 that? The thing that's kind of annoying me is, oh right, we can view the floats down here. I forgot. We can view the floats in this weird, like, hard to read readout that it does. So okay, XMM3 is the one, oh, so there it is, right? And we actually have 2 copies of it, right? Because 1 over 255 is this 0.003921, right? That value. And so it looks like 392. Well, that's not exactly right. So I'm not sure where it actually is. Let me see here. I was just trying to figure out where our values action. There's the clamp. So I'm not sure where that inf255 was actually happening. That's very confusing. Because I feel like it should have been loaded, but negative 3.7179, right, is not the same value. I'm not sure what the compiler fanciness was doing here. Right? These are not, they're close, but they're not exactly the same. So I'm not sure what it was doing there. I'm a little confused. So if we take that inf255, oh! Did it do some, no? I don't know what did it do there? Do you guys know what it did there? I'm not sure what it did there. As opposed to figuring out what it did with the square, I'm not sure what it actually even did with the constant. Right? Because I'm just trying to figure out where it loaded the actual value that I would have expected to see there. Right? And I do not know. Because this is not that constant, it's a close, but it's negative and it's not exactly it. So I'm not sure where it actually loaded that constant. And so I guess what I might do too is I'd like to look and see where it actually loads that constant in, if it ever actually generated, or if it generated some other constant. So let me see if it actually ever even stores that constant. So it might not have done that, right? Yeah, so I don't know. So the answer with the square is I don't even really know what it ended up doing with this code in terms of how it's doing the multiplication by inf255. I don't know what it's doing there. It's decided to do something decidedly more advanced than what we asked it to do, but what that thing is, I couldn't actually tell you. Maybe you need somebody who's better at assembly language trickery than I am to know what the compiler decided to do there and whether or not it was a smart thing or a dumb thing, if that makes sense. What is at RDP plus H? Oops. A bunch of zeros? So is that actually giving me the value? I'm sorry I'm not talking more, but I actually do not know what's going on. So that is actually correctly RBP minus 10H. So it's actually loading into XMM10 a bunch of zeros, right? That's just what it decided to do there. Yeah, so I don't know. And in the extended registers, in the upper registers too, I don't see the value in here either. XMM10 is just a bunch of zeros. Mul-PS 8 and 0. So it's multiplying those two together. What's an 8? We still don't really know what that value means, right? Let's see here. XMM 8. Is there a way we can see XMM 8 as float? God, this is so awful. Let me see here. How do I, please let me view the registers? Why can't I view the registers as float? There's got to be some way to view the registers as float. That's the floating point registers. That doesn't help us. I just want to view, right? I mean, is that so wrong? I just want to view. These are showing me as doubles, which I don't want to see. I want to see them as floats, here we go. This is what I'm looking for. There it is. Okay, so it was just using the extended registers. It's just using the top 8. Okay, thought I was going crazy there for a second. Man, this register view is worse than I remember. All right. So anyway, here is where it loaded the value in XMM8. So what it's doing here is the multiplication of XMM8, and it looks like this is probably going to do one of those. So it's loading XMM8 in there. It's multiplying both of these guys, XMM10, and so it's doing 2 mults. This is doing 2 of those inf255s, right? It's then loading a bunch more guys in, right here. There's one of the squares. That's squaring a value. So this multiplied by the inverse 255. Here's us squaring the value. So that's good. Here's us squaring the other value. So it did this totally right. Here's where it did the multiply by inverse 255, right? it gives those a little bit of time to complete. So it's hiding the dependency, okay, by inserting some moves in here, right? Then it's doing the square right there, right? So it doesn't compute the value twice. Now it's doing, here's where it's doing the inf 255s for the new guys that moved in, gets those in the pipeline. And then it's moving some more guys in to registers. And then I don't know where it's doing. Oh, it doesn't have to do the square for the alphas. So it's just moving new guys in, and now we're on to other stuff. So yeah, sorry about that. I got confused because I forgot that I forgot about the top 16 registers to check them. For some reason, I was like, well, it's got tons of registers down here. But yeah, obviously, it doesn't care which registers it uses. It might as well use the higher registers, whatever. So yeah. And ABI-wise, it's probably smarter for it to use the higher registers anyway, and that's a whole nother story. Anyway, so yeah, it looks like it's doing exactly the right thing. It's loading these guys in, it's doing the multiplies, and it's hiding the latency in the multiply by doing other stuff, and then putting, just so in case the processor, even if the processor couldn't have, making the window a little more favorable, it's doing moves to hide the latency in the multiply, and then it comes back and does the square. So it's doing totally exactly what we want. No complaints there, even though it took me a little while to actually figure that out. So yeah, check that out. Look at how fast that's running compared to how fast it was running. Right? I mean, you can just feel the difference. It's pretty cool. All right. Where do OpenCL and other GPU frameworks fit into optimization? It seems like if something is SIMD-able, it could just be done wider on a GPU. Are there workloads that are better suited to the CPU and SIMD? So the answer is really that it's usually more about transfer time and about the degree to which things fit the pattern of what GPUs do. So to give you a little bit of a perspective on how this sort of stuff goes, GPUs are set up as, GPUs are set up as stream processors. What they want to do is they want to be able to move stuff directly in a streaming fashion, operate on it, and stream it out, right? That's what they want to do. Things like read, modify, write, they're very bad at. Like, they don't want to do things where you're doing a lot of work on things in place or scattered, right? Where you're like writing to random parts of memory a lot. They hate that sort of thing. Furthermore, control flow, they're awful at. They don't do that very well either. And so there's basically, CPUs are very good at general purpose kinds of stuff where it doesn't fit that super concise stream in, op, stream out format. And to put this in some perspective, if you take a look at a modern GPU, and you look at GPU, general purpose GPU workloads, the Xeon Phi, for example, which is a bunch of x86 cores on a die, apparently annihilates GPUs at doing general purpose workloads. Like, that's what everyone buys the Xeon Phi now. They don't buy a GeForce card, right? If you're doing like actual general purpose workloads. And so I feel like in general what it boils down to is how well does the thing you're looking at working on look like a stream processor that has a very known set of ins and outs, that's very like compact and doesn't do a lot of scattered read and write kinds of operations. How closely does it resemble that? If it resembles that very closely, then a GPU may be a good choice. If it doesn't resemble that very closely, then a CPU or one of these special purpose cards that's like a Xeon Phi kind of a thing that's a lot of CPU cores on a dedicated memory thing, maybe it looks better, right? We have optimizations still on. Yes, optimizations are still on O2. Why are there optimizing options in the compiler if one will end up typing SIMD functions? The answer is because that's not really what optimization means when you turn on optimization in the compiler. So what optimization in the compiler means is basically try to generate reasonably good assembly language for what I typed in, right? And it does not include vectorizing, usually, because the degree to which the compiler has to know what your code is doing in order to vectorize it well is a little beyond compiler technology tends to be at the moment, is what it boils down to. It's not to say that maybe someday in the future we won't have auto-vectorizing to the point where it actually can do all of this stuff that we just did, but right now that's not the case. So what optimization usually means is actually go through and try to write good assembly code, which takes longer and is harder to view in the debugger, right? Versus when I turn optimizations off in the compiler, it's saying, write exactly what I wrote down and store it to the stack all the time so we can inspect it easily and so on, right? So that's really what OD and O2 switch between. It's like, whether I want you to write brain-dead literal translations of my stuff into assembly that are easy to debug and slow, or whether I want you to really think about it and try to write good versions of the assembly, but don't really change the effectively what the code's doing. That's what OD and O2 mean. If we want to do creative wide SIMD stuff, the compiler doesn't know how to do those things yet. Do you know of the mm set RPS intrinsic NPD? Note the R and set R loads the values in reverse order, i.e. the order that is more intuitive. I have seen those. I don't ever use them because, again, it's just a question of remembering how the order goes. And if I remembered the order, I would know which way R went. Like, I'd still not remember which one was which, probably. Like, is R... Because it says reverse order, that makes me think it's going to load it in big endian. But the reverse is true. Reverse order actually makes it load it in little endian. So it's very confusing to me. Orlando Bloom, when do you think we will thread the renderer? We won't thread the renderer probably until we actually get a single thread pixel fill working well. So we got to finish getting these pixel fills working really well first. Possibly misguided question, is there a way to overload operators to use SIMD instructions instead? Yes. The problem with it is the compiler may not understand what you're doing, right? Like you just saw, we had a 50 cycle penalty for just using a vec2, right? We used a v2 instead of writing it in scalar, and it cost us 50 cycles in a 179 cycle routine, which is crazy. Again, almost a third of the cycles and at least a quarter of the cycles gone just for using that. And so I never do stuff like use overloaded operators with SIMD because I never know if the compiler is going to get confused, because oftentimes it does. Is padding and alignment still something you have to concern yourself with? I remember doing SIMD in the mid-2000s, and SIMD was essentially worthless much of the time if your data wasn't aligned. So I guess the answer to that is I don't know. When I learned SIMD programming, like you, alignment was of paramount importance. And so I still tend to align everything. But I guess what I would say is, even just based on what you saw today, SIMD was clearly very worthwhile, even though we haven't actually taken time to align stuff. So I guess the answer must be that actually alignment, while possibly still important, is obviously not as is not paramount, right? Addendum, by concern yourself, I mean, is it something the compiler now handles more automatically when you engage SIMD? Ah, yes. So I believe the compiler is now always smart enough to do stuff like align the stack properly so that your SIMD variables are not loading unaligned. I believe it does do that properly. And so that may be, if that's what you're talking about, I think that does happen properly now, yes. Will you generate ASM for Neon? GCC seems to be pretty bad at generating correct code with intrinsics, from my experience on Android. I don't know. I have never optimized on Android. I did optimize a Neon thing once. I didn't really super optimize it. I really just had a code generator that I wrote, output it to Android, to PS Vita, which is Neon. But I've never really had to look at it too closely. So I don't know. I'll ask Jeff and Fabian what we will need to do there. But that's a long ways away. How would you know if doing something will speed up the code, especially when it's a fairly large change to the code base and when time is limited? I find myself reluctant to perform such optimizations in fear of introducing bugs. Well, the answer is I try to follow that process that I was talking about before, which is get statistics, which we did, right? Figure out where the code is slow, which we did. Build a model of what the code has to do, which is what we're in the middle of doing now. So pretty soon we'll have this routine in a SIMD format where we can look at all of the instructions and know how fast it should run, and then see how close we can get to peak, which is what we'll do. Following those steps, it's kind of hard not to succeed at least a little bit. I'm not scared of introducing bugs because, I mean, I don't know, if you can't be confident that you can rewrite some code without introducing bugs, I think that's probably a concern that you should address more head on. What are these bugs that you're introducing? Are they because you're being sloppy at coding, or are they because the code that you're trying to fix was very poorly written and it's hard to know what it's supposed to do? Could you write some tests? Could you revert to unit testing, for example, to make some unit tests that will call the code that you're trying to optimize, and go ahead then and rely on those unit tests to catch problems that you're going to introduce? Like, look, what can you do there, right? And I would tackle that very head on, because I don't think you should be scared to optimize your code. That's not a good idea. That's not a good place to be. What do you think you'll next want to convert to SIMD in case I want to practice over the weekend? Well, so if you want to practice doing something simple with SIMD, and you don't want to push forward on SIMDizing this stuff, because I think I haven't explained any of the tools that you'll need to do that. So I think if you wanted really hard assignment, get this done in SIMD. Get rid of this for I loop if you want something real hard, because that will push you well beyond the things that I've taught. If you want to wait for me to teach that, then what I would say is we've already done everything you would need to know to go SIMD optimize the thing that draws a filled rectangle, right? We've got that filled rectangle here routine. Where is that guy? Draw a rectangle. So this routine right here, you should be able to write the SIMD version of this completely by yourself. We've already done everything that you need, right? And so you should be able to do the SIMD version of this entirely by yourself, with the exception of one part, which you could cheese out on, just like we cheesed out on it here, because we haven't gotten to it yet. And so you could pause on that part, which is the should fill part, right? We haven't shown how to do that. We're basically going to be doing some masked write kinds of stuff for that. But if you wanted to practice over the weekend, which is a great idea, I love the fact that you're even asking that question. If you want to practice over the weekend, take draw rectangle and SIMDize the whole thing except for that mask, that ending right part you can cheese out on if you want, because we haven't covered that. But this doesn't load any texture stuff. It's just writes. So you should be able to do the whole thing SIMD, just with the exception of that last part of the fill. Could you compile it OD and show how SIMD has helped there? Well, we can, but it's not really a useful measure in OD because, like, so we're 120 cycles right now, something like that. And if we switch to OD, right, you can see that it's 280 cycles or whatever. So it helps, but it's a problem because it still inserts a ton of cruft code in there. And so, compiling with OD definitely slows you down. Would it be a good exercise, albeit large one, to study a simple GPU and write some soft for it? Arduino or something ancient? I wanted to learn coding for GBA for a while. Basically, what I would say is getting more familiar with assembly language kind of code is always a good idea. I don't know that you need to go overboard with it, but basically what I'd say is whatever motivates you to do some assembly language programming. And when I say assembly language programming, even something that's just basically what we're doing here, which is like writing some intrinsics and seeing how they compile and making sure that you kind of understand roughly how that's working, just that alone is good. And so if you want to do some stuff like that, whatever motivates you to do it is good. If hacking on a Game Boy Advance is what will motivate you to do that, I mean, hack on an Atari 2600 emulator and write an Atari 2600 piece of code if that's what works. Anything that just gets you in the habit of thinking about registers, memory, machine, individual instructions, just that mental model of my CPU has actual things that it does, and every piece of code I write translates into that in some way. Anything that gets you in the habit of doing that thinking is good. So whatever motivates you to do that, do it. If that's hacking on a GBA, do it. If it's SIMD optimizing some code on Visual C++ on an x64, do it. Whatever gets you comfortable doing that, do that, and you will definitely be a better programmer afterwards. And your follow-up that says, let's rephrase, what CPU would you advise to study that would be simple enough yet representative enough of general stuff? I would say that doesn't matter. What matters is that you've connected the code that you write with the fact that there is a real CPU with actual characteristics executing it. Because CPUs change every year, right? So it's a constantly evolving knowledge. It's like saying, what GPU should I study? It doesn't matter. These things change over time, and so the important thing is that you build a mental model of the fact that there is a CPU down there, and that you know that when you have to start caring, you know what you'd go read, right? You'd go, oh, you know what? This code's too slow. I need to optimize it. I've never worked with this CPU before, but I know that there is this concept of a CPU that executes instructions and it's got memory and stuff like this. That's what we're about. Let me go read about that CPU. You'll read about it, go, oh, it's got a cache that moves in this way. Okay, it's got these instructions. Okay, it's got a wide vector unit. Okay, I see all these things, and now I've built a mental model of that CPU and I can optimize for it. That's what you want to do. So it doesn't matter what your first CPU is. Getting some experience with any CPU is enough, and then from then on, you'll always kind of be in the situation where you have to read about the CPU that you're on and learn some new things because they change all the time. So there is no such thing as like a representative CPU that is gonna like be the thing that you can always think about. That doesn't really work. How long have you been working on this, and when do you think you will finish? So I generally ballpark about 600 hours, which breaks down to about 3 or 4 months of if you were working on it full time. And we've done about 112 hours. Or sorry, 116 hours. So we haven't even gotten, we're only a sixth of the way through. So we haven't really spent that many. To put in some perspective, we're almost 3 weeks of full-time programming work in, and 3 weeks of programming is very little, right? So yeah. Are you going to optimize gameplay code as well? Probably not that much, because it probably won't be the bulk of the time that's spent, but we'll see. There might be some, like the collision detection or something might want to be optimized. Have you heard of the JStation 2 project from Jasmine Kessler working with the Raspberry Pi 2B+? I have not, no. Alrighty, I think we have come to the end of the stream and the questions. So let us go ahead. Let us go ahead and close things down. I feel like we should be pretty proud of ourselves. even though we haven't really taken too much of a look at things, our debug code now runs about as fast as the as the optimized version did, and the O2 version now with the SIMD in there is now running real time, right? Like we're totally running. I think we're running 30 frames a second now, right? So that's pretty great. You got to feel pretty good about that, right? At least I do. So yeah, we've got a ways to go still before we finish SIMD optimizing that stuff, the pack and the unpack and all that. But you should feel pretty good about yourselves. We're getting there. All right, and that was only 1 week, right? That was 5 hours of programming we did or whatever, right? 5 hours of programming to go from could not even run to running actually at frame rate. So I don't know. You guys should feel pretty good about that. Anyway, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. I hope you have enjoyed our optimization, and we've got another week of it coming up next week where we're going to take a look at some more advanced stuff. Basically, the load and the store part, and it's basically true of almost everything you write in SIMD. As you saw today, making the math run in SIMD is almost trivial. I think anyone can do it. It's really easy. Once I tell you a couple things, I feel like you should just know, right? I mean, that was pretty basic, because it's like if you see a time symbol, you replace it with a mul PS. That's it, right? The hard part is that the top and the bottom, because as you'll see next week, they don't fit the model of SIMD very well, and so you're constantly doing, especially on x64, which has limited instructions, on SSE2 anyway. The AVX 512 coming down the pipe actually has a lot better stuff for this, but in SSE2 anyway, it's really very cumbersome to do that pre and post work that we need to do, and you'll see we have to start getting into some talking about permutations, rotations, and stuff inside the vector, inside those vector registers, and it's just a little more complicated, and you're going to see it's a little more annoying. But it's, again, even that is not that hard. It's just annoying. You'll kind of see what I mean when we get to that. Yeah, please join me next week for that, because once we have that in there, our routine, I think, will be running actually pretty quickly. And then we'll just have to take a look at the cache loads for our textures and stuff to make sure we've got that working relatively well. So anyway, thank you very much for joining me. I hope you join me next week starting Monday. We'll probably be at 5 p.m. Pacific Standard Time starting on Monday next week, I suspect. So I hope to see you all back here for that as we continue our optimization of the software rendering path. In the meantime, if you would like to play around with the source code and practice some optimizations on your own, if you pre-order the game on handmadehero.org, you can go ahead and download the source code and work along with me. I upload it every day after we're done, so it's always up to date. So definitely check that out. Also, we have a forums if you want to ask questions outside the Q&A, or you want to take a look at ports to Mac or Linux and stuff that's up there. There's a bunch of good resources on the forums. Check it out. We have a Patreon page if you want to subscribe to that. It's a cool place to go just in terms of supporting the video series. Very much appreciated. And we also have a tweet bot that tweets the schedule, so if you're trying to catch a stream live, please check that out. It always lets you know when we're going to be broadcasting. So that's it for another week of Handmade Hero. I'd like to give a shout out to all the moderators who hopefully now all have their wrist guards, their official Handmade Hero wrist guards that I sent out earlier this week. I think everyone's gotten them now, so at least I hope so. So please enjoy them, and thank you very much for all of the hard work you do in moderating the streams. I know moderating the Twitch chat can be very trying at times. It's always a bit of a zoo in there. So thank you for keeping it relatively sane. I know everyone appreciates it very much who's trying to actually pay attention to the stream and ask real questions. And I know I appreciate it very much because I don't even want to know what the stream would look like if you guys weren't there. So thank you very much. And like I said before, we also will, the wrist guards aren't it. We will also be trying to do some other nice things for our moderators going forward with some of the Patreon funds. We haven't really figured out what that's going to be yet, but we appreciate what the moderators do, and so we'll definitely be trying to figure out some other good things we can do for them so that their work is not thankless. All right, everyone, take it easy. Hope to see you back here on Monday. Until then, have a great coding weekend, and I'll see you on the internet.